Okay, so once again, good morning to all of you. So now we are going to start our first lecture of this GYAN course on chalcogenide based phase chain memory for non-volatile data storage. So the first lecture is on chalcogenide based phase chain memory for non-volatile data storage. So the beginning is a basic kind of thing, just to give idea about, and then subsequently this lecture 2 on this memory applications and other. Subsequently, as per the schedule, we will proceed. So now I request Dr. Andre to continue with lecture 1, please.
No, it's not on. Oh, is it on? Now it's on. Can you hear me? Yeah, that's nice. So, good morning everybody, and welcome to our GYAN course lectures on chalcogenide-based phase change memory for non-volatile data storage. So, just a few words where I'm working and where I have come from. So I come from Germany, from Leipzig. This is the map of the Germany. You can see it, and the city Leipzig is located in the eastern part. It's close to the Dresden or to the Berlin. Just for you, just for. So my institute, I'm from Leibniz Institute of Surface Engineering, abbreviation RM. It's from Germany, Institute für Oberflächenmodifizierung. And our institute is located on historical place. It's just on Permoser Triangle. So you can see it if you draw here the lines. This forms a triangle. And there are here many research institutes. And one of us, we are also located here. So this is my building where I'm sitting here. This is the so-called LINA, Leipzig Nano Analytics. So it's dedicated building for transmission electron microscopy. We have here TMs and SEMs in this area and behind. This is big microscope, and this is the offices for students and for me. The city Leipzig is also nice. It's also a very historical city. This is the picture of the center of our city. This is the highest building in the city, and this is also historical place. This is the church, and it belongs to the university. It was built during the Second War, and it was rebuilt with new design and architecture. Last year I did workshop on phase change memory materials, and here in this building. So we have also nice monuments to the Battle of Nationals. It was built in 1914 after the First World. So now let me continue from the outline of our first day. This is the so today I will be talking about memory technologies and memory device architectures. And here in this part of my lecture, I will focus on 2 parts, on semiconductor memory, and on the second part on the phase change memory device architecture. So in the first part, I will summarize on the basic level the main memories, what we have here nowadays, what the manufacturers are applying or developing. And then in the second part, I will mainly focus on the device architecture of phase change memory. So now, just for you, if you are really interested and you are really inspired in this topic after this lecture, or maybe somebody of you are already working in this topic, there are actually 3 books on this topic, which I can recommend you. One book, it's written by Matthias Wutig and Simeon Raux. It was, I think, the first book published in 2009. Then the second was written by Kolobov and Tominaga in 2012. And then this book was written in 2018 and edited by Andrea Radeire. these all names are very famous in these phase change materials, and these are all leading scientists. And this guy, he's working at ST Microelectronics. So this is a very nice book on device physics, reliability, and applications. Also, there are e-books of these three paper books. But also be aware that knowledge about phase change materials is constantly developing. So you will find a huge number of papers which published every year by many groups, by many groups. Many of them coming from China because they are really interested there. There are many groups and dedicated laboratories and institutes on development of this technology. And I also took some information from many papers and original publications shown at the footer. So let me start with memory technologies and memory device architecture. So just let me say why do we need these new memories? If you look to our laptops or smartphones, we have already memory there, so we use it. But why do we need a new? So as Dr. Shredder Pandey said today morning, nowadays we live in an era of big data. The amount of digital data is rapidly increasing. So this is the estimation of how many data will be produced in 2026. It's written in this white paper. So here we see the increase up to 220 terabyte in 2026. I do not know really. We can maybe calculate in this year. So we have steady increase in data creation and use, and this all this data which we create now, maybe 90% now they are located on servers and on platforms like YouTube's, and they should be processing online. So, but nowadays technology which is based on von Neumann architectures, it's not so fast. And it's also energy demanding. It was developed, actually invented in 1945, and is energy inefficient because energy is now, the price for energy is now steadily increasing because of different issues in the world. I don't want to speak about this, but if you look to the von Neumann architecture, this is the idea of this. So in this architecture, that the processing unit, CPU, it's a logical unit. It's separated from the memory. If we want to make mathematical calculations, we need to the CPU should go to the memory and then take information, process, and then go back and so on, and then we get the output. So these all instructions and data are stored in memory unit, and there is a sequential data exchange between memory, CPU, and storage. And all processing being done by the CPU alone. And this is limited information flow rate, so the instructions are carried out only at the one time and sequentially. It takes time, and it requires also energy. So what would be the solutions? There are several solutions. One solution is to use processing in memory technology. Here we have again CPU, logical unit, and we have memory, but it's connected to the logical unit. So we can process also some mathematical operations in the memory, and it will save our time. We can also do everything in real time, and we will have real-time insights, immediate actions and response. And this is more energy and time efficient than a von Neumann architecture. Advantages of processing in memory is faster data processing and beneficial for real-time applications. However, there are many challenges. It's a design challenge, manufacturer complexity, because we need to integrate logical unit to the memory, and cost. So it's still expensive. Now, just let us look to the architecture of our computer, how it's built on. So we need and to the latency of the main components. So our computer they actually built from storage and memory. Storage and memory. So storage it's based on the HDD and SSD, and memory it's like DRAM and SRAM and the CPU. So if you look to the time access of CCD and HDD, this is like in the range between 10 milliseconds and 10 microseconds. And here for memory, it's in between 5 nanoseconds up to 10 nanoseconds. So we see that we have a really gap of 3 orders of magnitude between the memory and storage. Which is like about 3 times orders of magnitude between memory and storage. This gap it can be filled by storage class of memory, or it calls universal memory. And SCM it's based on emerging technologies. And universal memory or SCMs, they are proposed as device having the performance of DRAM or SRAM, and they are non-volatile as flash, but the cost of DRAM and or NOR flash. Now, if you look to the cost of different technologies, so the storage it's inexpensive, as you can see here. This is price per latency. And the price in gigabyte. And here the memory of course it's expensive because you need here lithography, and but the SCM is located somewhere in between, so it can some days maybe replace and fulfill this gap. The problem also with our memories, SRAM and DRAM, this is volatile memory. As soon as we switch off the electricity, the informations are lost here. And this SCM memory storage class of materials, they are non-volatile, so they keep the information after the electricity is off, or the power supply is off. So now, let us consider emerging technologies for memory computing. They are resistor-based memory resistors. So this PIMI, they're based on memory resistors. And memory resistor is an electronic device. Those resistance depends on the history of the electrical signal it has experienced. So as you can see here, there are many technologies which can have these properties like memory resistors. The first is ferroelectric random access memory, FERO. The data storage here is stored by polarization direction in ferroelectric field. Then ferroelectric field effect transistors. Here data storage is stored by polarization state of the gate dielectric. Magno-resistive random access memory. Here the stable remanent magnetization states for data storage. Resistive random access memory, formation root of conductive filaments, and the phase change memory is also in this list. It's based on Joule heating or phase change materials. Also there is the types of PCM which based on resistive switching or formation of filaments. I will talk about this. So now let us consider some requirements for memory technology. So in order to meet the requirements for competitive non-volatile memory, resistive switch needs to switch as fast as some nanosecond and electrically excited with only a few volts. The resistance state should be not changed while applying a read voltage of few hundred millivolt up to 10 years. And lifetime of 10 years and switching times less than 10 nanoseconds gives the unlimited endurance of 10 to power 10 to the 16 cycles. And this, of course, can be only achieved by switching mechanisms that scales highly nonlinear with an external stimulus like voltage. But there is problem in every memory technology that we cannot fulfill this in one material or in one device, because there is always a compromise between the write cycling endurance, energy efficiency, and data retention. So just an example, if you have a device which can have high data retention and high cycling endurance, it can be power inefficient, or it can have slow write speed. Our task is to find maybe one material and to build one device which can fulfill these all requirements to some extent. So now let us consider performance of different memory materials, memory technologies. Let us compare them with existing memory technologies like volatile memory, SRAM and DRAM, and we will compare to this all emerging technologies which are non-volatile memory. So if you look to the right and the race in time of different technologies and compare it with PCM, so the time is now on the nanosecond scale, but this SRAM and DRAM, they are still very fast. The problem is with many technologies, it's the energy consumption, especially for PCM. It's can achieve like 3 picojoule per bit, but it's still larger than for SRAM. But it's now on the level of DRAMs. Endurances, they are all fulfill this criteria except FIFET, but we need endurance like 10 to the 9 cycles, and it would be enough. And you see many technologies fulfill it. Then the cell size. This is the minimum cell size which can create. And if you compare the SRAM and DRAM, the emergent technologies, they can use an even smaller footprint, like PCM, VRAM, MRAM is like on this scale, but they can be smaller. Operating voltage minima, so they're all in this area range of like 1 to 5 volt as required for SRAM. Here you can see this is some data that I found. And data retention, of course, SRAM is volatile, and DRAM also. And for our memory technologies, it's like 10 years which you need. So if you compare all technologies, phase change memory technology with other technologies, we can find that PCM, they have benefits like better endurance as NAND, smaller footprint as DRAM, VRAM, MRAM, and FIFET, non-volatile compared to DRAM, SRAM, and it's also low at scaling. You can scale it like in 3D, so it brings low cost. But there are still issues like drawbacks of PCM, and this one issue is the high energy consumption, high as for SRAM, DRAM, and VRAM. So now let me consider the basic operation principle of different memory technologies. And first I will start with flash memory, or its field effect transistor. So the field effect transistor consists of based on silicon, of field of silicon, and there are also drain and source, which are doped silicon and doped silicon. And the storage element, this is the floating gate element. Here, this is polycrystalline silicon, and it's here. This is yellow. This is the silicon. This is dielectric. And we have also control gate polysilicon. So then the field gate filled with electrons. We can get written state, logic 0, and then we moved the electron from the floating gate. We have erase operation, and this is the logic state 1. The write operation is achieved by injection of electrons to the floating gate by four-folder Nordheim tunneling that occurs by applying a high voltage between 10 and 15 volts across volt line and substrate. here if you apply, you can inject some electrons. And arrays, this is large negative voltage which applied to repel electrons from the flooding gate by grounding volt line and applying 20 volts to the substrate, and as a result the electrons are removed from this transistor. And read is applied to volt line. Here we use smaller voltages as for arrays or writing. So the disadvantages of these technologies: it's a slow writing speed. It's a strong function of oxide layer thickness of this oxide layer. It's low endurance due to degradation of oxide layer caused by high electric field needed for the tunneling. Here we have during the cycling degradation of this layer. This is the limiting factor. Here we can reach the fields like on the range of 10 V per centimeter. And we have also read in blocks. However, this is standard technology. You see, you can get very small devices of that, and this is very cheap technologies because it's based on silicon, and silicon, this is everywhere. It's a simply sand, and you can make from that a silicon. So it's from silicon oxide and wafers, and then this technology. So now some emerging technologies. One is magneto-resistive random access memory, or MRAM. So in this technology, it uses magnetic tunnel junction. This is the device type. This is one transistor, one magnetic tunnel junction. Then working layer in such devices. This is ferromagnetic layers, which based on the cobalt, iron, boron, magnesium oxide, cobalt, iron, boron. But for these devices, you need a crystalline layers. So you need to heat up your system like up to 300 centigrades for layer crystallization, and some process, some technologies, they are very sensitive for such thermal, for additional ex situ thermal heating. But this technology is CMOS compatible, but very complex. Here, just basic principle of this technology. Here we have two ferromagnetic layers. One is free layer and one is spin layer, and they are sandwiched between a barrier layer, insulator layer. In this case, this is NGO. And if you apply external magnetic field, and then in such devices, the pinned layer is always pinned and shows magnetization only in one direction. And we will call this state like low resistance state. And this free layer, it can change their magnetization based on the application of external magnetic field. If we can apply here, we can switch this the magnetization, then we can put our device to the high resistance state. So because the electrons cannot tunnel for the barrier layer, and it brings the device to the high resistance state. There are devices based on this technology, like sold by Aerospin. It's very expensive technology. Just if you look to the price, for 1 gigabyte, you pay like 100 euros for 6443. And just if you compare to our DRAM, it's like 4 gigabyte you can buy for 7 euros. So it's very expensive, but it's used for in aerospace, automotive, medical devices, smart energy, Internet of Things, and storage solutions. So because it's non-volatile memory, and we need it, and there is a market to this technology. Now let us consider ferroelectric random access memory. Here the device, it's based on the effect of ferromagnetism. So here we use a ferromagnetic layer which can change the polarization up and down. One example is lead zirconium titanate, simplicity. And if you change, and these materials can change the polarization by application of external magnetic field. So if you can apply like polarization in this direction, the central atoms, oxygen can move, and then we change polarization. And if you just change, we can go the state down, so we can get 0 and 1. So we have here this polarization stage, the states, and it's used for information storing. So by right, we apply electric field across the. Here it's a simple capacitor. One transistor, one capacitors. We need 2 layers, 2 electrodes, and one ferroelectric layer. So this is also. There are advantages and disadvantages of these technologies. One advantage this is poor scaling of PZT, so you cannot scale it to a thickness of like 20 or 30 nanometers because you lose the effect of ferroelectricity. But maybe hafnium oxide, this is new ferroelectric materials which can be used for this. And also, one requirement for such technologies, you need epitaxial or highly textured thin films to achieve this high polarization. And it also requires thin film technologies and grow at elevated temperatures. So there are also some manufacturers of such devices. This is Infineon, which produce these such FRAMs, and again application, special applications like for portable and implemented medical devices, fitness tracker, monitors, programmable logic controller, or whatever. So now let us consider working principle of ferroelectric field transistor. It's similar to the FET we considered above. But in this case, instead of using floating gates, we used a ferroelectric layer here, you can see. And polarization in this layer controls the charge density in FET channel. And channel is conductive then B, this polarization vector points to channel down states. And if channel is non-conductive, then P vector points to the gate. And here again ferroelectric materials which are used. This is PZT, hafnium oxide, or some semiconductor layers, indium selenides and 2D. Advantages: it's a low cost if based on hafnium oxide, but high cost if based on PZT. It's non-volatile. Low power, high speed, but in all cases you need crystalline layers to have the ferroelectric effect. And applications, it's aerospace, automotive, medical devices, IoT, consumer electronics. I did not find the products to this FET, no information, but there are some developments and some like products in lab. In this small company, ferroelectric company, which are in Dresden. So now another semiconductor emerging technology. This is ReRAM or ARRAM or ReRAM, and there are two types. One is valence change memory (VCM). It's based on ion migration, and another type. This is ECM or CBRM. This is based on cation migration. These are also very simple technologies, CMOS compatible. Here let us consider the VCM. Here we need 2 electrodes and 1 layer where we store our information. So this working layer can be like tantalum oxide, hafnium oxide, also tantalum oxide, strontium titanate or titanium oxide. And here the principal idea is based on the formation and rupture of oxygen filaments. So to form these filaments, we need to apply the forming step. So we need to form this filament, and we have this consists of oxygen vacancies because they are mobile comparing to the cations. And so if we can create and rupture the filament, we can reach here low resistance states and then the high resistance state. This is technology. This is very simple stack because metal insulator of metal, low cost, CMOS compatible. We can reach different operation, multi-level capability, non-volatile, scalable, fast switching, low energy consumption, and operation power. But the problem is here the stochastic filament formation and necessity of forming step for this filament formation by applying a higher voltage. So the next memory device based on this effect, like filament formation, this is ECM, electrochemical metallization memory, or CBM, conductive bridge random access memory. Here, instead of like here metal insulator metal, we need one active electrode. So here in this case we will form our filaments consistent from the active electrode. And in this technology, the electrodes, active electrodes, it can be like electrochemically active electrodes like silver, copper, or nickel, and the counterpart electrode can be standard like platinum, iridium, tungsten, or gold. And thin film is a solid state electrolyte or ion conductor. And here the effect is also based on anodic dissolution and cathodic reduction of the filament. Again, in this case, we need to apply a high voltage to form first the filament, and then we use this filament to achieve low resistance state or high resistance state. Again, here the advantage is that this is very simple stack, consists of anode electrolyte cathode. It's low cost, but again the problem is the stochastic filament formation and forming step. So stochastic filament formation, this is not a non-controllable process, and this is one limitation. The companies maybe do not like to use such memories, but anyway, there are some products based on VRAM. I found for Fujitsu. You can see here one product. So now let's go to our phase change memory, to our main topic of our lecture. This is also emerging technology, and this is very simple technology. It has simple design, and it's CMOS compatible, non-volatile, but it's based on Joule heating process. So let us consider two PCM cell designs. One which is commonly used. It consists of two electrodes, top and bottom electrode. Then there is a heating elements which embedded into the silicon dioxide, and this is a phase change memory material. In my course of lecture, I will use abbreviation like PCM for memory and PCMM for phase change memory materials. In the literature, you will find like a mixture of the PCM or another. So now the next design of such which PCM can be used, it's like CBRM, as we have seen before. It's based on active electrode and bottom non-active electrode, and there is a phase change layer in between. In this case, the chalcogenides, they are fast ion conductors. In this device, you can also achieve analog and digital behavior. Analog behavior, it's interesting for brain-inspired computing. And these advantages of this device comparing to other CBRAMs, that here you don't need no forming step, so you don't need the application of high voltage to form the filaments. The conductive paths are already there. and here it operates at low voltage, so it's we can save some energy. Now to the working principle of standard PCM technology. It's based on the phase transitions between amorphous state and crystalline GST state, and you can achieve it by application either optical or electrical pulses. So if you apply low voltage pulse to the amorphous state, you can bring your system to the crystalline state, and if you want to go back to the amorphous state, you need to apply a reset pulse with higher amplitude, but with shorter duration time. Then what happened here? You melt your material during reset to the temperature higher than melting temperature. Then, if you can achieve very high cooling rates, then you bring your system to the amorphous, back to the amorphous state. For that operation, you need you apply a pulse voltage, which brings your material to temperature higher than crystallization of material, and then you can crystallize your device. For read operation, it's clear you need a pulse with really low voltage in order not to affect the states, set and reset states. So set operation, this is right. It's transition from amorphous to crystalline, and it calls logic state 1. Reset, this is erase. This is transition from crystalline to amorphous state, and it calls logic state 0. And to achieve this amorphous state, you need high cooling rates. It's on order of 10 to 9, 10 to 12 Kelvin per second. And read is achieved at low power. So now what happens if you go from one to another state? The material, phase change materials, it undergoes structural transition, and also changes their properties, physical properties, like optical constants are changing, and sheet resistance is also changing. Here you can see the N and K constants, optical constants for this is amorphous state, and this is for crystalline state. So they are different, so the reflectivity of both states is different, and also the absorptions in both states is different. For electrical memory application, we are more interested in the sheet resistance, and if you look at amorphous state, it's a highly resistive state, and the crystalline state in this area is a low resistance state. And we have here like a 5 magnitude, orders of magnitude drop in resistance during the amorphous to crystalline phase transition. And this huge difference in the two states we use to store the information. So the contrast in optical and electrical properties enable data storage device utilizing these phase change materials. So the effect of phase change memory was actually introduced by Ushinsky in 1968, and he showed in his work 69 that you can switch these chalcogenides by application of electrical pulse. It was really high energy pulse, but he showed the main principles of this memory device. And of course, because the industry is searching always to new materials, to beyond the silicon, there was a really huge development in material development in this field. There are a huge number of compositions which the the research institutes or companies tested. And then in 1987, the Japanese group, they discovered germanium telluride, antimony telluride system, and they showed very stable switching between this state. After that, there are three main classes of phase change materials which currently used for phase change recording. These are alloys based on germanium telluride and antimony telluride, also doped antimony telluride and doped antimony alloys. After inventation and discovery of these phase change materials, it was shown that they also can be used for optical data storage. At that time, we had a CD disk which can be only, you can write the information, but they were not readable. So these materials, they showed these effects, writing and erasing the information based on the crystalline and amorphous mark, and then based on the composition like AST, they developed, the companies developed DVD, RB, and Blu-ray discs. Because the crystalline marks, it has a high reflection as the amorphous mark, and so you can store the information here and there. So the phase change memory materials, these are tellurium-containing alloys or chalcogenide alloys. If you look to the diagram, tellurium, germanium, antimony, these alloys they are sitting on this tie line between germanium telluride and antimony telluride. You can find here different composition. This composition 2 to 5 is a prototypical phase change materials which employed in memory devices. But as I said, there are some issues with phase change alloys. One is thermal stability, for example, in this for these compounds. And to improve the thermal stability of such alloys, you can use germanium-rich alloys that you can increase the crystallization temperature of your materials. This is for application in embedded applications like aerospace or automotive. So now some history of the products based on phase change memories. As I said before, in this year there were a huge development after the invention, 1968, then 1977. There was a first product, a CDRV, the 1600 megabyte. Then 21 years later, there was a development DVD-RV with 4.7 gigabyte. This is 2 layers, and then in 2003, Blu-ray discs with capacity of like 33 gigabyte. And then in 2005, ST Microelectronics introduced the first, one of the first phase change memory device with 4 megabyte memory. 2006, Samsung developed 512 megabyte. 2008-9, there are also further development up to 1 gigabyte on 45 nanometer CMOS technology. And then Samsung, Micro, Western Digital also use it. And in 2015, there was also huge development and invitation of Intel Micron. This is a joint development of 3D X-point memory based on phase change materials. So now, as I said, little bit said before, there are some drawbacks of phase change materials. One is on the device side, but it can be somehow managed by the industry. But some properties, these are internal properties of every material, and you can, if you know this, you can somehow manage this or reduce this. One is problem, this is the resistant drift. The resistant drift, this is the problem of amorphous state, that the resistance can be changed over the time. So it starts to increasing. The amorphous state is relaxing, and then it goes to the higher resistance state. And this is the problem. the problem if you want to build your device with multi-level capabilities. So if you want to store them more than 1 bit per cell, like 2, 3, 4, or 5. Another problem, this is the thermal stability. The phase change, they are crystallized at really like low temperatures, 140, 160 centigrade, and it hinders its application in embedded devices. It has still switching speed, it's still slower than DRAM, but crystallization kinetics it limits the set time. And energy consumption, also one issue, like melting of crystalline phase is necessary for reset, and non-uniform heat of loss, which also contribute to this problem. And it has relative reset current density. It's like for GST, it's on the order of 20 mA per square centimeter. But this is, as I talked to some guys, this is normal value used in CMOS technology. So it's high, but it's still somehow, if you can reduce it, it would be nice. But it's still good and used in CMOS technology. So now let us look to the material parameters and how they impact on device performance. For example, crystallization temperature and thermal stability on amorphous state, they impact the data retention and memory lifetime, or so-called set power. The melting temperature, it affects the reset power. Resistivity in amorphous and crystalline states, it affects on-off ratio, set and reset current. Threshold voltage, it affects set and read voltage. Thermal conductivity in amorphous and crystalline states, it affects set and reset power. And crystallization speed, it affects set pulse duration, and of course power, and data rate, and amorphization speed, its reset pulse duration. So there are some material requirements for phase change memory technology. One is that the set speed should be less than 100 nanosecond. Reset current should be like on the order of less than 200 microamps. Endurance more than 10 to the 8 cycle, and long data retention like 10 years, more than 10 years at 85 centigrade, and higher temperature for embedded memory. So as we can see that a large set of material parameters can influence the device performance. These properties are mostly linked to the chalcogenide composition or materials. We will consider it during this course of lecture. And of course the size of phase change material and of device impacts also this all performance and properties too. And we will also consider how it affects. So now a really short summary on semiconductor memory technology. So steady state increase in amount of data, the amount of information we create doubles every 2 years. For normal bottleneck, it's a sequential data exchange between the physically separated memory, CPU, and storage device. It wastes time and energy. In memory computing is an emerging technology for energy and time efficient computing. And emerging technologies for the memory computing are resistant-based memory resistor like PCM, VRAM, SST, MRAM, FSM, and ReRAM, ECM, ReRAM. The combination of fast switching and unity to last read disturb is also known as voltage dilemma. In order to fulfill both requirements in one device, its switching kinetics should exhibit a non-linearity that is large enough to span these more than 60 orders of magnitude in time. VRAM, SST, MRAM, and PCM are already commercialized, while FIFET is on the way, like FMSC in Dresden. And PCM technology has several advantages compared to VRAM and SST-RAM, but also many advantages which are interesting for the application. So now let me consider the phase change memory device architecture. I think because I don't have enough time, I can start and we will continue afternoon on this topic. So first, let us look to the recent or so-called melting current. If we let us look the design of our cell, which consists of bottom electron and top electron. That this is GST, and the height of the heater. This is heater. Here, this is length of heater, and this is the area of heater, and this is the length of GST. And each this is metal heater, sometimes tungsten or silicon nitride or whatever can be used here. And the GST and this heater, it has all the properties. So the recent current in PPCM it defines like it's equal 1.5 of melting current, and the temperature in hot region it's given by T, the rise of temperature T0 plus this is power of dissipation, and this is the thermal conductivity of the system. So according to the Joule heater, power of dissipation is equal to the resistance ohm and current, and this ohm is equal to the resistivity of thermal resistance of heater and thermal resistance of GST multiplied by I. Now we can also rewrite R ohm as thermal conductivity of heater and as length of heater divided by the area of heater and plus conductivity of GST, electrical conductivity of GST, and length of GST divided by the area of GST. This is the area that the phase change occurs. Now overall thermal resistance from the hot spot to the heat sink is divided by the thermal resistance of heater and by the thermal resistance of GST. And this thermal resistance of heater can be divided as 1 divided by K, and LH divided by AH. This is the thermal resistance of GST. It's defined as 1 divided by thermal conductivity of GST and length of GST divided by the area of GST. Now, if you assume that this is a melting current, and if we apply some mathematical operation to this system, we can obtain the melting current as the square root of T melting. Here it will be the T melting minus T0 divided by R ohm multiplied by the overall thermal resistance. And this is the thermal resistance that we can put here, then rewrite by using this equation. We can get this large equation, and here also then. And what we can see here, first that the melting current depends on the cross-sectional area of heater, here on the size of heater, here on the cross-sectional. Also it depends on the material properties of GST, like K, which is thermal conductivity, and also ρ, which is just the electrical resistivity, and also the length of both the heater and the GST layer. Now let us make some assumptions, like if the air ohm is controlled by the heater, or all resistance, if it's just controlled by the heater, then we can neglect by this part, by this term, which is related to the GST, and then we can get the melting current, which is a function of A and L, and also of heater, and also resistivity of heater, and K and heater and K of GST. So if we apply isotropic scaling, we can see that our DH, this is the size of heater, then in this case it will be proportional to the two-thirds of footprint. So the melting current, it's like will be approximately proportional to the footprint. If we consider our system without heater, if we just have two electrodes and the GST layer, then we can neglect by this term, so we don't have a heater here, and then we can see that the resistance resistance depends on the material properties of GST, and then the melting current. This is the properties of simply of GST, like dimension, length, and material properties like K and Rho. So overall, IM, it depends on geometric properties, thickness and contact area, and also material properties, electrical resistivity, conductivity. So I think we have 1 minute left. We can use this time for questions, and afternoon I will consider with this topic of device architecture. So please ask questions, if any.
So any specific doubt, or if you have any query, you can discuss. The session should be interactive. I mean, whatever you are thinking, it could be basic question also. You should not hesitate, first of all. So here expert is here to discuss about this, technology, basic understanding. So because just he started with basics, the basics of that fundamental of PCM technology, how it could be processed, what are the types. Okay, it is not involved with phase change. He has given a detail about MRAM, FERAM, okay, some other technology also, and then finally he is going to enter into the phase change memory. So memory, it's a very broad domain, you are knowing that, and each and everyone is using in your laptop, computer, even cell phone. So you may have some questions. So that you can think about those things, and then the session should be interactive, as I'm telling you here. Here we are not here just to deliver and you just take, you are right, okay, this is fine, but you should have some query, and don't think that if I'll put any question, so what is this question? No, it should be not like that.
Yeah, but don't be under the pressure. I'm here around for 5 days.
Yes.
If you just think I have some question basic, just ask me. As I said, I'm the whole day, 5 days I'm here. Just come to me. I'm here in the guest house or here. Yes. So just, I'm here. I can maybe show more. I have more information. Just, if you're interested, of course.
Hello, sir. Good afternoon. There's a wonderful introduction about this course. And I have a small query about if a
yes. So I have one query about if we're doing electrical resistance measurement, from that measurement the slope itself is showing the speed of the phase transition. Is it shall we compare, is possible to compare between the two samples while only looking on the thermal electrical resistance graph? The slope will give the phase transition speed or not? That's what I was asking.
Yes, you can compare, but in this case, in the phase change memory technology, you apply pulse. You need to, so it's not constant pulse. You need to apply pulsed electrical pulse. And of course, you will have some different, some spreads in the values of resistance between one device and another device. Depends on the materials, because it's can be not uniform. So it's a normal.
Okay, so we cannot take a speed from the electrical resistance measurement.
You take the speed from your pulse.
Okay, good.
So from the pulse generator. Then you can think about the speed. This all data I showed you, it was just simple full probe measurements. Here you cannot extract the speed. You cannot extract the speed of phase change. So the speed is measured really by device, by application. And then by measurement, changing the properties. I will also show you one is how to measure using the optical setup. I will show during lecture, or by application of pulsed electrical pulse. Then you see the change of the resistance from high to low resistance state or back.
We can identify is any intervening phases having hormone from this graph listed.
Yeah.
Again, please.
So, Professor, like what we show is like from crystallized metastable state at some point of time.
Yes, it's also possible, because multi-level capability we'll see. You can achieve if you apply sequential pulses to the, for example, to the crystalline different amorphous state, and so you can induce different resistance states.
All right.
So it's based on the volume change. So you change the volume and you change the resistance of the device. So you can achieve this by application of
Thank you.
sequential pulses.
So lasers can also generate the phase transition, right?
It can also generate the phase transition, right? Other than electrical pulses.
What? Sorry?
Laser.
Yes. Yeah. Optical pulse.
Optical switching.
Optical switching.
Yeah.
Yes. It's like either optical pulse or electrical pulse.
Both are we are using.
For electrical memory, it's electrical pulse. For optical memory, it's optical pulse. So it's laser. Actually, laser. Yeah. I will also show you some examples more on the optical switching, and maybe you will show some electrical switching.
Yes.
So,
So I think not then Andrew will be here, so you can have some of your questions. We have a time. It's not like that. Just think about the topic. You may have some questions. You can discuss. He will be available. So possibly we are covering multiple aspects, like some of this multiple electrical switching and all. So subsequent lectures will be there. You will get more idea on that. Okay. So let's thanks to speaker for introduction of this. So now, after this break, we will again meet at 3 o'clock, our next lecture, and then we'll continue with this other topics. Okay, thank you so much.